Thank you, Patrick, and please let me know if I should not be audible. And thank you for having me. It's exciting. I learned a lot the last 2 days, and I'm a biochemist by training, and our lab is interested in how do the flows of energy and matter shaped by your cellular metabolism govern the out of equilibrium behavior of cells and developing organisms. And at one point, when we think about it, right, like if you want to grow, you need a lot of energy and mass. But what is maybe less obvious to some is that even if we do absolutely nothing, we will die if we do not eat, right? Or a cell will die, or an embryo will die if it doesn't eat. And why is that? That's just, of course, because of the second law of thermodynamics. If we think about our cells, it's very structured and ordered. And if we would see a cell in isolation, it would seemingly defy the second law of thermodynamics. Of course, we all know that our cells and organisms, we do not function in isolation. We are an open system and a dynamical chemical open system operating far from equilibrium. So the cells continuously must consume energy and matter from the environment and spend free energy to the environment to increase the entropy of the universe, to maintain order, propagate information. And of course, if we stop eating, eventually our cells and organisms will decay to equilibrium, and we will eventually die. And this phenomena, to ask whether to what extent do the thermodynamic properties of living system relate to biological function, is kind of like a very old question. And at one point, Alfred Lotka, who is famous for the Lotka-von Terra model of predator and prey, he already in the 1920s proposed in these two back-to-back articles that maybe we can view evolution in the light of the laws of thermodynamics from first principles. And if you look at his work, what he proposes is that the organism which traps the most energy from the environment and dissipates the least amount to the environment should automatically have a fitness advantage and prevail in the light of evolution. And similarly, much later, Ilya Prigogine thought that his approaches to irreversible thermodynamics could also be applied to embryonic development or biological function. And this idea now, we came together at one point, and this is nice concepts, and we came together in 2019 at the Kavli Institute at this workshop for cellular energetics. And at one point, we started to define some key questions like, how can we start to tackle the relationships between thermodynamics and living systems? And we defined a little bit like three fundamentally open questions. I think what we argue is that we currently do not have a quantitative understanding what are the energy fluxes between biological systems and their environment. And then if we look, for example, in cells, or what are the key energetic costs of cellular processes? And if we could measure these fluxes, can we now start to understand to what extent do energy fluxes or matter fluxes constrain biological function or cellular processes? And what we try to do now is to bring together people from very interdisciplinary fields, on the one hand, working on your metabolism, which is kind of the engine of energy transforming system in biological systems, the cell biology, studying how cellular processes work, together with the idea of stochastic thermodynamics and non-equilibrium systems. And so what our lab in the last 4 years started working on is a little bit on the scale of developing embryos and cells. And we work on different scales in terms of embryonic development. And what we usually do is we use calorimetry in order to measure the heat dissipation of cells or developing organisms. However, what I would like to spend today's talk on is something we were thinking about in collaboration with my theory collaborators, Pablo Sartori and his postdoc Tommaso, where we were thinking about what are the thermodynamic constraints to unicellular life across evolution. And this is a data-driven approach. We use experimental data, but the idea, what we are thinking is, what we want in the future is, can we somehow find a relationship between any biological function and its dissipation? And what we started to look at is unicellular growth across microbes. So if you think about, is there any relationship between, for example, an E. coli cell growing, and making 2 E. coli cells, between its dissipation and how well it can grow? So one point is like, how do you even start to think about the dissipation of a cell, right? So at one point we were thinking maybe we could use the idea of what's a steam engine, right? We need not to know each individual piece of the steam engine in order to understand its thermodynamics. And also the contributions to thermodynamics we can know is say we can understand the thermodynamics of this engine by knowing the high temperature, the low temperature, and the amount of work the system is doing. So if you now think about a cell or an organism, our engine is our cellular metabolism. And at one point, this is this interconnected network of thousands of different chemical reactions, which on the one hand does two things, right? On the one hand, it extracts energy from the environment, and we call this catabolism. And on the other hand, it's building up all the molecules which make up all life, which we call anabolism. And on one hand, from chemistry, we know that the thermodynamics of an individual reaction we just can describe by the Gibbs energy change of a chemical reaction. But at one point we were thinking maybe what we can do is we can take a bioengineering approach where people looked at and they coarse-grained down whole metabolism of a growing population of cells, ignoring individual reactions, and just similar to Carnot, look at the input and output fluxes of chemicals, energy and matter. And what people have shown, at least for a yeast cell, this is sufficient to describe the thermodynamics of a growing population of cells. So at one point, Pablo and I, we thought this is a very nice concept. Maybe we can generalize this. And we were thinking about, let's assume a population of cells, and we have, you need to consume substrates, and you release products, and you make biomass at one point. So at one point, we can form a mass balance around the system. So biology is not nuclear physics. So all the elements coming into the system in these substrates are consumed, must come out of the system, or they are conserved in this additional growth of biomass. And at steady state, assuming that a maximum growth rate, the system is in a quasi-steady state, we can write down the dissipation or the entropy, the second law of the system, in terms of the heat exchange and the chemicals exchanged, as well as the biomass entropy, which is conserved in the system. If we now write down the first law of thermodynamics, the enthalpy, which is contained in the substrates, minus the enthalpy, which is released in the products and conserved in biomass, will give you the heat. And if we now use the definition of the chemical potential and put the first and the second law together, we can describe the dissipation of the system in terms of its free energies and the chemical potentials of these substrates and molecules. And at one point, this free energy change of this overall macrochemical reaction needs to be negative. So this free energy is dissipated to the environment at a constant temperature, then increases the entropy of the system. And this is very nice, and you can write this down, and it's quite straightforward. But at one point we were thinking now, can we now design experiments to measure all the exchange fluxes of energy and matter between a biological system or a growing population of cells? And this is what we were worked on the last 4 years, but we also thought maybe we can apply this framework to already existing data of the last 80 years of unicellular microbial physiology. So how does such a data look like? So imagine now you have an E. coli cell population growing aerobically in minimal media in a batch culture. So at one point, your E. coli cell grows exponentially, and it only has one carbon source, which is, in this case, glucose, which is the carbon source in the electron donor. It has an ammonia source and oxygen. And unfortunately, a lot of data doesn't report all the fluxes we would need in order to report the full flux space of the system. What is usually reported is yields instead of fluxes. And yields are usually defined as the ratio of fluxes. So as a disclaimer, we use the unit of time here because we always work with ratio of fluxes. So at one point, for example, what people report is the biomass yield. So how many cells, so how many E. coli cells in terms of the carbon moles you get per mole, for example, of glucose or electron donor consumed. And so we use ratio of fluxes. And in this way, what you can write down is a kind of a macrochemical equation where now the stoichiometry of the fluxes are yields or normalized fluxes. At one point then, what you can do is you can use elemental balance in order to solve for the other yields of the system. And with this, we can then write down the dissipation, not in terms of fluxes, but in the terms of yields. And we can use tabulated free energies of formation of all these molecules. and the free energy of formation of biomass, which you can estimate, in order to calculate a normalized dissipation, which is the free energy change normalized per the moles of electron donor conceit. So at one point, this is very nice. And what we did now is that for a lot of data, we can then go in the literature, postulate these macrochemical equations, solve the yields, and then use chemistry databases in order then to calculate the free energy dissipation of the system, the heat and the entropy exchanged. And we have roughly about 590 data points in our database. So at one point, this is very nice. And this is, for example, how such a reaction looks like. And this is very well characterized in terms of the free energy change of the system. So at one point, of course, you can postulate anything, but at one point you need to validate your approach. And the first thing is we looked at the free energy change or the entropy production of our data case, and it's satisfied. So the free energy change of these reactions is negative in 99% of the cases. So we excluded the 1% of the cases. And then similarly, the law of Hess tells us that the exchanges in enthalpy of the system equals the heat dissipated of this chemical process. And beautifully in this bioengineering literature, we had about roughly 100 data points where people measured the amount of heat released per unit of biomass made. And this is what you can see here on the y-axis. And we can compute theoretically from our macrochemical equation the enthalpy change of that reaction. And this is what you can see on the x-axis, and that's the equal line. And that adds very, very nicely up. So we can nicely, the computed enthalpy change and the measured heat dissipation adds up very nicely. So validating this approach that we can coarse grain down all the complexity of metabolism into a simple reaction, and the heat dissipation of the system matches really well. And then let's start to explore our data set. So what do we have in our data set? We have many unicellular archaea, prokaryotes and eukaryotes. So we have all domains of life. They're all unicellular. We have autotrophs, so they fix carbon, CO2. We have heterotrophs, which use, for example, glucose as a media. And we have all kinds of very different metabolisms, from classical aerobic respiration to methanogenesis and so on and so forth. And so the first parameters we look at is the dissipation, and the other thing is a growth parameter, which is the yield. So if we now look at the yield, what you can see here is the data grouped by different electron acceptors. So for example, the electrons usually go to oxygen in respiration. Inorganic is when you do fermentation, if you make, for example, ethanol. Inorganic is if you use other metals, or if you, for example, fix CO2. And you can see across the data set, there's roughly 2 orders of magnitude spread in the yields or in the growth of these different organisms. And similarly, the dissipation is similarly variable over about 2.5 orders of magnitude across these different organisms. However, now, if we start to plot the dissipation as a function of the biomass yield, you can now start to see that they are linearly correlated over about 2.5 or even 3 orders of magnitude. And the slope in this log plot is not different from 1, so it's also linear in linear space. And what we can then see here is that we have very different kind of metabolisms and different kind of organisms across this spread across these different metabolisms. However, there seem to be some linear relationship which points towards the idea that the slope of this curve, which is the dissipation divided by the yield, which we call the dissipative cost of growth, seems to be conserved across very, very different types of organisms. So this tells you that whether you are an archaea or a eukaryote growing either in a hydrothermal vent or here on, in the lab, you always have to dissipate a conserved amount per unit of biomass you made. No matter how big you are, how fast you grow, this is somehow conserved in the system. And this is what you can see here. This is just the mean data. And just to give you a little bit of a number, this is roughly about 500 kilojoules per carbon mole made, or 20 kilojoules per gram, or about 210 kT per carbon atom fixed, or 8 ATPs. And at one point, you can see that across these different metabolisms, there seem to be some conservation, but there seem to be also a spread within certain types of metabolisms. Um, um, and I come to this in a little bit. But at one point, I just also wanted to show you I have a very little bit of data regarding where we have chemostatic data, where we have enough fluxes, and now we can plot it in the unit of time. And what you can see now here is the heat dissipation rate per unit mass made against the growth rate. And roughly the mean dissipation is roughly about 0.9 watts per gram made. But you can also see that at least here it's linearly correlated, supporting the notion of this conserved cost. And similarly, if you look at quantitative heat dissipation measurements, we can also see that they're linearly correlated. But now you can start to see that these methanogens are very different in terms of their heat dissipation towards their free energy dissipation. So this tells us a little bit about the free energy dissipation per unit biomass may be conserved, but the way you do it may be divergent across different organisms. So at one point, to tackle this question, we can start to now disentangle the dissipation and the contribution of the heat dissipation. But since they're also exchanging molecules which have an entropic content, there's also chemical entropy change associated with the exchange of molecules. For example, you take a glucose molecule and you make two gases out of it, the entropy is going to increase. So now we can look across our data set, how do organisms, although this dissipation per mass is conserved, how do they allocate the dissipation between heat and entropy? And so at one point, what we do have is, for example, organisms which absorb a lot of entropy, so they feed on gases, and they have to compensate by dissipating mainly in the form of heat. On the other hand, we have heat-dominated dissipation, meaning that this is your classical respiration, is what our body is doing. We do dissipate mainly in the form of heat. However, if you now do fermentation, you produce alcohol or acetic acid. These fermentative metabolisms in the absence of oxygen dissipate roughly half by heat and half by entropy. And then we also have predictions that there is endothermic growth, meaning that these acidoclastic methanogens, they actually function as a refrigerator, absorbing heat from the environment, but then have to compensate by producing a lot of gases to increase the entropy. And there's an N1 calorimetry experiment out there from the 70s where people measured that actually these acidoclastic methanogens grow endothermically or absorb heat from the environment. On the other hand, what you can see is that although this is across, this cost is conserved across organisms, there's variability within various types of metabolism. And at one point, if you group them, what is the electron acceptor? So who accepts the electrons? You can see that we can separate organisms which grow in the presence of oxygen. They have this negative relationship between dissipation and biomass yield within its metabolism. And all the other organisms which do not grow in the presence of oxygen seem to be invariant. So this is, at one point, we can look at the deviation, and you can see this very nicely. The round dots are all organisms which grow respiratorily in the presence of oxygen, and all the other ones are organisms which grow not in the presence of oxygen. So what oxygen gave you, or the evolution of oxygen gave you, is this idea that you have a trade-off between dissipation and yield, a negative trade-off. And these organisms can reduce their dissipative cost compared to others. And this is what we call, empirically, what we find, this is the slope of this relationship is what we call a cost correction factor. So until now, what I've showed you is that across metabolisms, we can describe the dissipation of the system as a linear relationship between the cost and the yield, and the costs seem to be conserved across organisms. And then within organisms, we can see that oxygen aerobic respiration allows you to reduce dissipation, increase yield, via negative dissipation yield trade-off. So now at one point we were wondering, can we now characterize these two metabolic signatures following the formulism of thermodynamics far from equilibrium? So at one point, of course, we know that at one point we described the dissipation as the sum of the products between yields and their chemical potentials. But these yields are not independent of each other, because they are constrained by element conservation of your metabolic network. So what we can do is we can decompose this dissipation into the independent contributions only, where each of the products at one point is the independent yield. For example, this is usually the biomass yield or the electron donor yield, but since we normalize the electron donor yield to itself, it's 1. And at one point, we can define then generalized thermodynamic forces Ri. And we have 2 thermodynamic forces, which is RED and RB, which itself is a combination of the chemical potential of the dependent chemicals. So in a way, you can think of the free energy change of your energy yielding reaction and the free energy change of your biomass composition. Sometimes we do have facts where there are more independent yields, but usually in about half our data set, we only have 1 independent yield, which is the biomass yield, Y here. And for the others, usually the other independent yields are neglectable. So at one point, we can then identify 2 fundamental thermodynamic forces. And at one point, this is what we call RED, that's the electron donor force, which can heuristically be associated with your catabolic or energy transforming reactions in your biological systems. And that usually is opposed by another fundamental force, which we call the biomass force, which is usually opposing the catabolic force, which is the free energy you need to overcome in order to make a unit biomass. So at one point, what we then purely empirically find is that these fundamental forces, usually this catabolic force approximates really well the dissipation we calculated in the first place. And somehow, if you plot now this catabolic force against the biomass yield, you can still see this linear relation. So somehow this conserved cost lies in what we think at the moment lies into this in the chemistry of your catabolic reaction network. And usually this anabolic force, which is usually negative, so it shows you that it's opposing your catabolic force, we find empirically that that approximates well, which is this cost correction factor we've shown before. So what you can see here, this cost correction factor against the biomass force, you can see that most non-respiring organisms have a low opposing force, and oxygen at one point opposes growth by a larger thermodynamic force, and we have some interesting transition states. And so therefore, since the sign of this opposing force, since the sign of REB is an opposing force, it really highlights the notion that even growth is a classical free energy transduction system. And it also allows us now to define a thermodynamic efficiency of our system, which is now the measure of the free energy produced and consumed by the independent yields. And what we can see is despite opposed by a larger anabolic force, aerobic respiration is more thermodynamically efficient. And it's interesting to note that the maximum is around 50%. But with this, I just want to end here a little bit. And what we've shown is that we have different metabolisms across very different kinds of organisms, but they all have to dissipate roughly the same amount of free energy in order to make a unit biomass. And we think that the origin of this conservation somehow lies in your catabolic metabolic network. The way these organisms do this dissipation is very versatile, and you can do that via either heat or entropy. There's a large anabolic force opposing anabolic, and yet they are thermodynamically more efficient. And of course, what we are doing experimentally now, we measure all these exchange fluxes. We can apply this now to growing mammalian cells, and similarly here, mammalian cells dissipate half heat, half entropy. We apply this to multicellular growth models and embryonic models, and we also have now light in the calorimeter to see whether we have whether photosynthetic growth, which is missing, is also behaving similarly. And with this, I'd like to thank you, and I'm happy to take any questions.